Hello, I am continuing where I had come so far in my earlier presentation or lecture. One of the first thing is saying from a simple two-dimensional flat representation or earlier engineering drawings, we have now progressed towards 3D. The advantage of 3D being that it is easy for us to conceive something in a product like this. No, we can conceive the product very well and try to manufacture it, and using the same drawings which we have made, it is possible to now go ahead and produce the parts in large numbers, and at this point we will end up with something which is what do you call developed very well and everybody understands about it. One of them is making things for mass production. You have two ends, two extreme options. One option is if they are in reasonably large numbers and strength and such things are not that important and you can tolerate certain changes in thickness, you can go for plastic injection molding. Allow me rather at this minute not to think about saying yes they can be made in so on and so on like that. One variation of this, if you want strength, is to use injection molding or die casting in a metallic devices. So, all your automobile things and all are typically non-ferrous die cast materials, and in the case of this is a simple, I will say inexpensive plastic injection molded part. The problem comes is normal times there is no issue at all in dealing with this thing, but kindly remember that this space which is a cover, lot of detailing has gone into it, and this of course is a professional piece. This what you call wireless thing is a professional piece, hence lot of detailing and careful amount of things have been done, and the tooling for this and the material for this are costly, and it is constantly being improved. In this case, the enclosure is one part of it, then the electronics inside, and then the RF and how it the works and all is another type. And if you come to toys, there are very inexpensive toys where things are made with really low cost plastics. Now, one thing you will notice is this has been made in two different settings, but miraculously these things match. How do they match? This is where this whole lecture is about general type of fits and tolerances. Kindly look at my monitor. One of the things you will notice is this has been derived from actual practice. So, this in a comprehensive way this has been given, all three fits are shown here. If you remember, I mentioned this about how to fit a bearing into a housing. So, this is the actually the starting point. If you notice here, there is something has been done here to make sure that any bush, usually it will be a bronze bush or otherwise called gunmetal, it is made out of a one type of bronze material. Traditionally this was then earlier, and this itself is directly a bush which is used for various bearing type of applications. So, in fact, you have bearing material separately, the processing, then the metallurgy itself is slightly different. It is a softer material and it runs well, and then there is something about the tribology of it saying how it takes oil and all that. So, you will see the outer part of it is called an interference fit. So, you push something and then you almost force it into that slot. And the other side we have here a clearance fit. A clearance fit is actually something which is rotating inside. See, in this there is a beautiful option for it to rotate. We are not going to put a separate ball bearing or anything here. No, there is no necessity of a ball bearing here. What is done is you make a sufficient amount of a clearance here. So, that is what the word clearance is. And the other extreme is a transition fit, meaning sometimes it may lock, sometimes it may not lock, and we add an extra another item for it to hold it in place. So, all these types are possible, and depending on this thing, this particular thing is a key, and there is a keyway, and then how we lock it inside is very, very critical. Now, if I come down, this is what I was trying to talk to you yesterday. So, you will notice here that the hole itself can have a range of what do you call permitted dimensions which come out based on the type of machining you use. Normally, if the machine is kept under one particular setting and the tools and all are good and the material is good and closely monitored, this follows a very average normal yield. It may be, I am not talking about the statistical thing about whether it is a bell curve, it is a normalized curve or anything, but it does follow certain things, what you call certain yield which you can get from the machine. Similarly, we have a shaft which goes inside like this. So, you will end up with a very peculiar thing saying this is the tolerance that has been given. This tolerance is represented here 0.5 millimeters, and similarly there is a tolerance which is given here, hole tolerances, that is also again an 0.5 gap is given here. Now, when you actually try to assemble any what you call the shaft to any of the holes, so something starting here, you understand, something starting here to this thing will be possible. So, depending on the process what is being adopted in the production shop, and depending on how you select these things and put it together, somebody has to have a good working knowledge of these things. Earlier it was easy meaning somebody will present it like this in a indication like this. So, this is where the what you call things what I talked to you about, saying there are norms that are there about the way you mention the what you call lines, the way you mention this sectioning, the way you mention your tolerances, the way you mention the elements that is there and so on, like this have been adopted separately depending on how things have been progressed earlier. In manual craft usually things are assembled together and little bit of running in is given. So, it does not matter if you are trying to make a grinding stone at home with a what you call an opening, and then you have a that grinding stone inside, it will behave one way, and things like a pestle and mortar, the things are very, very huge, there is no issue at all. But the moment we have come into the industrial revolution and you had to end up with large number of interchangeable parts, this business of clearance and tolerances has become very, very real. Now, the something which is very related to this is you cannot arbitrarily give anything you want here, because when it is produced in the machine shop, somebody has to set the machine and somebody has to inspect the parts, saying which is acceptable, which is not acceptable. This is where to make a little things a little more inexpensive, the concept of designating a batch came, saying in fact you can have all these things now, saying something which is on the lower end, something which is nominal, something at the higher end, and call it type A, B, C, D, where the fit is very, very critical, as in the case of a cylinder and a piston, or in the case of a cylinder liner, the whole thing is stamped on it. After the measurement is done, they stamp the designation on it, saying this comes under the class A, meaning this follows this and so on. But then normally earlier it was easy, you just had to make a drawing, probably dimension it and write what you think was a reasonable amount of thing directly. But now once this CAD way of designation came about, and especially both in the case of simple two-dimensional or drafting representation versus actual 3D assembly representation, all this is to be carried out with due care. You cannot independently change anything, you cannot change what is written there. If you change it, it leads to a lot of problems. This is where the full-fledged solid modelers with assembly and with various other checks have developed all these things inside. Automatically you can mention the class of fit that is required. Now go to the, let me to the transition fit. If you see here compared to the other one, you will notice here that both possibilities are there. So, if you take a shaft which is on the maximum diameter and then you take a this hole which is of the minimum diameter, under some conditions an interference can occur. Now it is for you to decide how to deal with it and so on. Right now I will not talk about it, I am just talking to you only about such a thing is called a transition fit. So if you go here and the way things are made, we tend to give some designation there, and this is where things have changed a little over the years. It is not correct for you to arbitrarily give what you think is a reasonable, what you call, way of mentioning these things. The problem being, to carry out this, both the operation, to carry out the inspection and trying to make the assembly, this will become very uneconomical for you if you keep on narrowing these allowances and the tolerances. If you keep, while it can, in principle you can make it 0, 0, 0 something, it will be very, very expensive to make such a thing. So depending on the type of running and the type of thing, we need to make something. Now you come to genuine interference fit. In the case of the interference fit, under all conditions, there must be completely joined together and lock itself fully. This is called a pure interference fit. So when, if you remember the first example, there was a bearing sleeve fitted into a plate. There, under all conditions, it should maintain itself well. Here various types of things are there. So Have a look at this nice interesting thing I have. Sir, can you please show this? See this. Oh, it has got merged in it, so maybe I should put it here. Very nice and interesting thing. Do not worry too much about the design. This has been made by a company and given as a nice go away compliment. I am trying to take a sip. Good. Water with or without spirit tastes good. Now, if I see this, this is made by another company. They are probably competitors. They have ensured that this will not fit this, and they have patented the thing. This thread and all they have patented. You got my point? From purely from commercial point of view, they have made a design by which it will not fit under all conditions, you understand, and naturally absolutely no problem, even by mistake if I do it will not come, which will make me come to a very interesting aspect of this fabrication of this. You will notice that this one is made by a what is called blow molding. Several of your toys, several of your things in your house, there is a particular die in which something is inserted and it blows, and variations here are very high. Understand, no? The amount of things what you get is variations are very high. Further, there is a tremendous amount of design involved in it. Same, I am not sure whether it is a PVC or polypropylene bottle, same polypropylene bottle when it is used for holding water under normal pressure, the thicknesses and things are different, and when you would like to put carbonated or soda or many of our colas and all that, these thicknesses are different, and cap is made by very traditional injection molding. You see here, this cap also is an injection molded cap, this is an injection molded cap. Now, how do you ensure that in all conditions any bottle will fit any cap that is there, and then given the small caveat that I said, this whole thing is made by blow molding and hence dimensions are not very stable. The issue is that is only part of the story. The part of the story is that this part of it is blow molded. However, the former that is required for this one is injection molded. If you see carefully, probably you will notice a flash, and then you know how the thing is opened and all, how it is taken from the mold, and then you will notice that these two, that perfect amount of fit has been ensured, and usually this thread formation also is very special, and then we have something here and whole thing sits perfectly. See that, because here the tolerances in the injection molding are very good here. This is slightly softer material, so it can actually take little pressure and expand and fit the thing. This remaining part is different. From here onwards, actually it is a former that is made. It looks like a long tube like thing, a little like an injection syringe. Then it is kept inside the what they call the injection mold, and then some gas is inlet into this. This is warmed up and it takes the shape afterwards, and various ways are there how to take it out and all. If you are curious, you can just look it up. But what I would like to say is that a very routine ordinary thing on the among your collection, this needs lot of patience in designing, and not just designing. Now, when we come to this, if you see the way we show it on the drawings, this is very clear. So, earlier I thought life was easy. All we had to do is we go to the fabrication shop, we will go to the supplier and ask him, what do you think is the best thing. So, I just erase, or I have something called a modification or change note here. I say this diameter 19 millimeters, the tolerances have been changed. But the moment this CAD system came, it is inconvenient to just go and rub out the dimensions and change it. Instead, you are expected to use a different thing. This is where comes to advantage of having solid modular CADs. If you take any of the things, large number of them there, but in the parts where we live, both the several of them, specifically SolidWorks, both of them are, I think, from Siemens as well as Dassault and so many other people make these new solid modelers with what is called associative dimensioning, bidirectional associative dimensioning, meaning if I change the dimension here or the tolerance here, the shape of this part and it changes automatically. Similarly, if I change the part, these dimensions change automatically, which helps in certain conditions we can look at it. The very professional things can also take care of various types of this tolerancing and fit for holes and shafts. You have seen something about this here, which I was trying to tell you all the time. Probably it did not make much sense, except people are actually in the field and this thing. If you had waited a little and this thing, you will know what it is I was trying to talk to you about. This is called a designation of a fit. So, nominal dimension has been shown here, saying it is a 50 millimeter nominal, and from the nominal letter designation, you will notice that capital H and 9 has been specified here, and in the case of the shaft which goes inside, a small lowercase letter and another number has been designated here. Combinations of this have been standardized with different types of materials, different types of operating conditions and so on. Occasionally, people write down the actual values. This will help in case you are making a small number of numbers and you have a screw gauge or some other or a profile projector with which you measure these dimensions, so that you know where we stand. You understand, no? Both the dimensions, the plus 062 and nominal, this thing has been mentioned here. In this case, in the case of shaft, while the nominal is 50 mm, what is designated here, you have seen this 49.920 has been given here, which is okay, people can read it and all that, but the thing is, this corresponding to this D9, these things have to be perfect. If somewhere in the previous drawing, if you change, we may end up with a little problem. And imagine this part comes under in one drawing, this part comes under in one drawing. Very difficult to manage these things every time. This is also acceptable. Instead of showing the nominal, the things have been explicitly written here, saying this is the thing, but the most preferred way is just to write the H9 and D9 designation. So, depending on your way of dealing and all that, for each of these we have thread gauges, we have go no go gauges, and coming back to my example of it, if you have a thread gauge, imagine this part of it has to be checked. Deliberately I have that thread gauge for this will have something like this. On one end of the rod we will have a little larger thing saying it should not go inside. If it goes inside, that means this is larger. The other end of it will be a little smaller, saying it must go inside. So, that will imagine I will try to get a picture of it. Imagine a large hexagonal holder, and one side you have a thread which follows whatever is shown here, another side you have another thread which follows the other designation. I can just quickly put it, take random sampling, acceptable quality level. If I get a bin of say 10,000 parts, I randomly select one, try it here and pass all of them. That is statistical. In statistical, it has been what you call designated, saying which should be a quality level. Further, if I go down now, you see here at the extreme, on the what do you call the whole, basic size has been maintained, what do you call has been mentioned here, and the tolerance grade including a letter designation and including a type of what is the type of fit that we require is mentioned here. H and all comes to things which are on one direction. Similarly, in the case of the whole, a smaller letter and then a different designation has been given, and which I was trying to tell you is generally this combination of this saying H8 F7 on 50 is the wanted fit. Now, we now come into an important thing. Will the 50 be the same in case, I am sorry, will H8 F7 be the same in case it is a fine screw? Extreme fine screws are probably what you like to find in a thing like your spectacle frames, or you may find in your pen, or you may find in your automobiles. You understand, no? This is extremely small, and in fact the diameter of this may be some 1.2 millimeters or 0.81, 1.2 millimeters. Is this the same for it? Yes, because the IT grade depends exclusively on the basic diameter. Up to say 0.1 mm to 0.4 mm, it is one range, and as it comes to 1 mm, and then from say every 1 mm after that, later on, depending on the type of trade, depending on the type of material and so on, these tolerances are catalogued and available in a book. In fact, if you open the thing, we have a huge table which shows the type of tolerances which are specified, and large manufacture for measuring tools, and then for materials, for fits and all that, no. So many of them have been specified. You understand, no? Not easy, it is tough. Tough. Here comes the, how do you select a particular tolerance and fit? It comes to this chart which I was talking to you about. It is a huge chart. So, not easy, is it not? As you go to the left, things are extremely expensive, very, very expensive, and then it goes to the right, things are little inexpensive. Understand, imagine you would like to make a something which you push into a wall, followed, no, something which you push into a wall, if you give a very tight tolerance, it is pointless, very, very expensive. Instead, if you give it toward the right, it is easy. That is how most of the dowels, most of the that plastic or wooden things which you push into a wall will be, they all toward the other extreme. Now, I feel you read this right now on your own, come from left to the right, you keep reading it, you will know. My voice may be a little irritating. So, you see hole bases, shaft bases and so on and so on. So, we have things like H11 C11 saying this is a loose running fit for wide commercial tolerances, allowance on external members. So, again once again simple commercial, very easy to achieve, does not cost too much money, and if you are starting from the what do you call I will leave you to read the bottom part toward the end of this. And locational or sliding fit, yeah, this is something which is quite important. Free running, not for use where accuracy is essential, but good for large temperature variations, high running speeds or heavy journal pressures. Loosely this has been taken from one of the what I call general engineering descriptions, but all of these are based on actual practices. You understand, no? Actual practices on how to make things work. Somebody has actually taken a bush, then they have found out they have run it on a typical, if it is a large number, they run it on an automate called a Swiss automate or any of them depending on where you come from. You have Bridgeports, and then we have any number of the small machines which quickly maintain all these things. On the other end we have accurate machines, close running fit, and for accurate location at moderate speeds and journal pressures. Typically your sewing machine at home may have this type of a close running fit. You see not many bearings the way we know, no, not many roller or ball bearings will be there in that machines. What will require is actually there is a bush and then you can rotate it, and usually there is a, in case there is a, let us say this is a bush like this, then there is a shaft which is moving inside, and usually that whole thing moves inside, there is a small opening for you to lubricate it. In that condition this is the best, and original Singer machines and all that, they still work 100 years after they have been made and sold on that, they work very well without the least amount of any problems. They continue to work like this. That is because somebody has paid attention to two details. One of it is the type of journal that you need it and the, how easy to achieve it, and the type of that sliding part inside like this. Now you may come to the things are so loose, how can we make these things work? There it is not every time things are made such that they are non-recoverable, non-repairable, or we can tolerate with the yield. Usually what is called a second operation including a reamer is passed on to that. If the shaft is made standard, we will not touch the shaft much because making there is a problem. However, if there is an opening, you can make what is called a proper reamer and adjust it to that. So imagine you need to make a 3.8 mm hole, probably it is made into 3.75, and you have a special reamer which exactly goes inside and turns, and when you take it off, nicely it sits there without any problem. So using this combination of, I will not call it rework, using a combination of second operation and using a shaft, it is possible for you to achieve much closer fits, and things work for a very long time, and a lot depends on the metallurgy, status of lubrication and how things work. Otherwise you will not be having all that old type of vehicles, old type of sewing machines, typewriters, and anything you have in your house, and if you are romantic about an old thing, they were made in small numbers and usually closely inspected and expensive at that time. But right now even you can buy a very beautiful combination programmable sewing machine, does not cost too much, it is much inexpensive compared to the old FAF machines or compared to now the various other machines. And similarly when you go into apparel work, they have machines which work at very high speeds, and you do not have a treadle or you do not have a hand, instead you have a big motor, and sometimes there is a pressurized case in which all the oil is recirculated, pumped inside. Hence things like if you take a tough material like jeans, or if you take certain huge curtains made of thick materials, they are just fed, and in one shot like it will be, things will be moving at great speed. The secret is what started as a almost handcrafted devices have now become automated. And why I am mentioning it, I am not deviating, I just wanted to tell you that all this is now possible for us to make. Instead of that manual drafting, if you make a proper 3D model, and if you mention these tolerances and elements, and if you also work closely with these various things that are mentioned here, medium drive for ordinary steel parts, or shrink parts on light sections, tightest fit usable with cast iron. You may have wondered how sleeves are fitted into a internal combustion engine. That whole outer casing is made of anything. Right now it is aluminum, otherwise earlier it used to be variants of cast iron and steels, and you have a sleeve which has to go inside. So what is done is the sleeve is kept in a cooled oil, and the casting is probably a little warmer than ambient, so that it expands a little while this is closed, and just by hand things are pushed. Once they are pushed by hand, they just lock permanently once the temperature comes back to the normal. And imagine that if you have a cylinder liner, it is always hotter than the usual ambient. Just after a little bit of running in, it sits permanently. There is no other way of knocking it off. Some of them have a provision of pulling it out, otherwise they probably machine it and put some other things. And coming back to this, things like pistons and the what you call cylinders, they come with grates printed on them, saying depending on the type of liner you have, or depending on the type of reboring you do, you can select a different piston, and even there you have piston rings which need to have these things. Me being a mechanical engineer, the stress is a little more on this. So we have here a big clearance fit table, and it shows under all conditions how things run and so on. Basic size at 1 millimeter, and it goes on and on like this, and then we have all these things which are happily, they work peacefully without the slightest what do you call confusion on the workshop premises. You can easily specify these things in the drawing. And now again one more time let me tell you, in the new type of software where solid modeling is done, there is a provision for you to include all these things in that. So you have seen that bush first drawing, if you see, if you remember, I will take you back to the very first drawing. It is possible now you mention a proper type of fit here, you mention a proper type of elements here, or clearance fit, and due to some optimization or something, let us say you decide to change the shaft, saying instead of a 6 millimeter shaft, or I will put it the other way, instead of a 1/8 inch shaft which is going to be 3 point something something, which will change to a 3.2, because the quarter inch is 6.35. So that the other shaft could be 3.175, and the new shaft we have is 3.2 millimeters, which is slightly different, or you may end up with a 3 millimeter shaft. Now you have the advantage of you can play with all these things, and at one place if you change, all of the other things will be taken care of. It also involves that you mention what is the minimum material that is required for the bush. So, the full fledged assembly software, all these things are peacefully built into the software, and life goes on without the slightest thing, life goes on peacefully. So, if I now go back to the most of our electronic enclosures end up with being made with sheet metal, and sheet metal by definition somehow it just means any flat sheet, but by metal by default is assumed that it is made with one type of a cold rolled sheet with a particular type of carbon composition which we call mild steel. So, do not be upset if you just say sheet metal and people give you something which is made out of cold rolled sheet. That is the common thing. Whenever somebody says it is made of sheet metal, it is like that, and added to that we also have, generally it also comes with various types of finishes on top of it. And why I mentioned finishes is cadmium has been found out to be dangerous. So, cadmium is not used anymore, but nickel is instead nickel, or in the case of if price is lower, zinc is coated like that. All these things including the zinc plating, including the what you call basic material, and depending on the types of processes that are used are very critical when we specify the various types of tolerances and fits on our dimensions. So, I will stop here, I will try to come back later on, I will just stop here and go back a little and then explain this to you in the next lecture. So far I have just talked about the very basic fits and tolerances and why it is important for us to put them into a drawing, because manufacture is not like just simply you make a drawing and somebody will work on it. If we do that, we will again be coming back to just maybe taking an old drawing and then trying to digitize it and then let things go. With the new provision we have, the original model can have all the fits and tolerances built into it, and when the file is transferred to the fabrication people, it can be directly probably what is called a machine codes can be generated it, and then the fabricated parts can be made out of it. So, I will come back to this later, which very big way things edge hold to the bend, okay. Bend to bend, what is the tolerances there, and then agural tolerances, edge to edge or hole to hole. If you recollect seeing workshop video, which was I think part of lecture 7 or 8, after the bending you see there is a very peculiar spring back available into that. So, they will try their best. In this case ours is a folding machine. At the back there are certain stops to ensure that if you compensate for the spring back, the part that comes out is practically usable. It is not 100% 90 degrees, but this tolerance of plus or minus 2 degrees are built inside. There are some adjustments in that which ensures that the lever which you are operating stops there. So, thank you. I will get back next time. Thank you.